Hello and welcome to this AQA Further Math Statistics video, the third in the series of Continuous Random Variables PDFs. If you recall what we looked at in the previous video about probability density functions, there are some important facts you need to remember about those functions. First of all, a probability density function will always have a value greater than or equal to 0. With continuous variables, the probability involved will always be equivalent to the area under the curve. That's the probability density function. And the total area under the curve will always equal 1. So if you just pause for a moment and read through this example. It's one we looked at in the previous video, but this time we are being asked to find the value of an unknown constant k. And that means that we have an idea that this continuous variable can be modelled by a straight line relationship, but we don't know the exact nature of that so that it fulfills the requirements of a probability density function. And the best approach to begin with something like this is to sketch the curve, and don't worry too much about the fact that you don't know the value of k. You can just pretend k is 1. And the important fact we need to use to find the value of k is that the total area under the curve must equal 1. And if we look at that total area under the curve, it's quite clear that when t is 10, f of t is going to be 10k. And if we look at this area under the curve, the area has to equal 1. And the area is clearly just a triangle, and therefore the area is going to be a half multiplied by 10, the base multiplied by the height. That must equal 1, and that gives us 50k equals 1, k equals 1 over 50. And as an alternative, you can still use calculus rather than just finding the area of the triangle. If we look at finding probabilities, we want to find the probability that t lies between 3 and 7, which is clearly relating to this area here. And finding a probability is integrating under the curve, or in this case the area is actually just the area of a trapezium, and therefore using the formula for area of a trapezium we would need to know the length of the two parallel sides, and this one where t is 3, the length of that would be 3 over 50. And if we look at the length of the other side, then t is 7, so that would be 7 over 50, and the horizontal perpendicular distance between those two parallel lines is 7 minus 3, which is 4, and therefore the area of that trapezium that must equal 1 is a half multiplied by the sum of the lengths of the two parallel sides multiplied by the perpendicular distance between them, and that will give you 2/5. And again, you could also do that using calculus. So if we look at this second example, again one that you met before, and we have a missing constant here, so imagine that we knew that a cubic function would describe the time taken to complete this race, but we're not exactly sure of the constant we need there to make sure that our function is a probability density function. So again, and you may remember we plotted this curve before, if we look at the probability density function, we need to work out the value of A such that the total area under the curve equals 1. And this clearly is going to be an integral, and the area under the curve between the values that we have for this particular density function is going to be equal to that definite integral. That must equal 1, and you might like to pause this and just check your working and go through that, and we verify or find that A equals 4 divided by 27. And here, if we want to find a probability, we are interested in finding the probability that t lies between 2 and 3. And in order to do that, this time we are going to have to find the area under the curve between 2 and 3. And so that's just going to involve, again, integrating that same function, but this time using the value of A that we've discovered and using the limits 2 to 3. And here you've got the integral worked out for you and the probability of 13 over 27 for the probability that t lies between 2 and 3. And finally, although it's not specifically in the specification, it's worth just noting that the mode that is the most frequent point will always be the highest point on the probability density curve, and clearly the highest point is where t is 10, so the mode is t equals 10. If you have a curve like we had with the second example, the highest point is going to be here, and that's going to be at the maximum turning point, and that will require you to differentiate the probability density function, put that equal to 0, and work out the value of x for which that function is a maximum within the range that's relevant. And you might like to pause here and just have a look at the workings here to discover that the mode is actually equal to 2. And that concludes this third video.